So now we're going to move on and talk about a new section, which is Riemann sums. So let's get into it and figure out what Riemann sums are all about. So what's going on? When we introduced derivatives, we said that they computed the slope of the tangent line of a function at a certain point. That was what we went with, and we were like, okay, this seems kind of cool. Integrals have to do with area under a curve, which seems a lot more exciting than finding the slope of a tangent line, I'll admit that. So we're finding area under a curve, which is very, very interesting. So if we're given just some random curve, if we're very lucky, we can just compute the area by splitting up the graph into some known shapes that we know well, and just use some geometric formulas that we know to compute the area. So we have a graph below here. We want this area underneath the graph and above this x-axis, right? And we have these like dotted lines that we drew in, and we're like, okay, I can figure out the area of this. That's just the area of a triangle. And then this is the area of a rectangle, so that's pretty easy. This is the area of a trapezoid, so that's also easy. Another rectangle here, and then that looks like a semicircle. So I can sum those all together. But as you know, not all functions look like this, and we're not as lucky. So how do we do it? When the graph is curved, we're going to use equal width rectangles to approximate the area. And this is what we call a Riemann sum. So let's take a look here. We have this graph. This is our function. It's like a parabola. And we're trying to find the area underneath this curve here. I'll try to draw it a little bit better. And we want like this total area underneath here. And the way we're going to do it is we're going to take a bunch of these rectangles and just shove them underneath the curve. And we'll say if we take the sum of these rectangles, the areas of these rectangles, that'll be pretty close to the sum of the actual area under the curve. It's not going to be exact, like we're still missing out on this area here, 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 and here, but it's pretty close, right? It's a good approximation. It's the best that we have. Rectangles are easy to work with. It's easy to find those areas. And this is what we call a left Riemann sum, because the top left corner of the rectangles touch the curve. So here, 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 those are the top left corners of the rectangles. Similarly, we can have a right Riemann sum. So we have the same function here, and we're looking at the area here, right? This is the total area that we're looking at. And we have rectangles once again, except now the top right corner of the rectangles touch the curve. So that's here, 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 here. And once again, what we're saying is that if we take the areas of these rectangles, that'll give us a good approximation for the area under the curve. So we have like this area, this area, this area, that one, and surely there's like a couple more here where it's like this, something like that, right? And we get these areas. And it's a close approximation, except now we overcount, right? We overcount this area. We overcount that area, and so on. So neither of these estimations are perfect, but that's why they're called estimations. They give us a good idea of what the area could be. And rectangles are easy to work with. So remember, left Riemann and right Riemann, we look at which corner of the rectangle touches the curve. Wonderful. So if we have a function that is increasing, like we just looked at, the function is increasing, then if we were to do a left Riemann sum, as shown in the picture, that area would be an underestimate, right? We said that if we take these areas, that's all good and dandy, but we're missing out on these areas in between here, so it's an underestimate. If we do a right Riemann sum, that would be this here. We get an overestimate, just as we pointed out with these red areas. So that's what happens with increasing functions. What happens when the function is decreasing? Well, now a left Riemann is an overestimate and a right Riemann is an underestimate. So pictured is the right Riemann. If we take this area, that area, and that area, that's great, but we're missing out on this, and this. And I guess I'll draw what the left Riemann would look like. I'll use, let me just use a bigger brush. So left Riemann, we want the left corner to touch the curve. So if we continue this line upwards, we touch the curve there, and then we want a rectangle, so the opposite side should be the same length, and then we get something like this. Same thing here, we're going to start going up until we reach the curve. So it's here, the lines overlap, and then we're going to draw the horizontal over, and then the vertical line. Same thing here, we keep on going up until we reach the curve, and then we can draw our horizontal, and then one more should do the trick. Here, here, here. So once again, we have 4 rectangles, and now their top left corners touch the curve. And if we take the areas of these, we get a good area sum, but we overestimate because we count this region, which we don't need. We don't want that. It counts this region, which we don't want. It counts this region, which we don't want. And same thing here, right? So that's an overestimate there. So depending on the function, depending on the left or right Riemann sum that we do, we either get an overestimate or an underestimate. But it's still, after all, an estimate. That's what matters. So how do we optimize the area? I mean, we're still doing an estimate, but we want the estimate to be as close as possible. So how can we optimize the area so that way we're as close as possible to the true area? The simple solution is we just use smaller rectangles, right? When we have these large width rectangles, we miss out on a lot of area because we have less liberty with the rectangles that we're using because they're just taking up so much space. So we can see here there's a lot of things going over the curve that we just don't want, or we're missing out on other areas. But if we use a bunch of smaller rectangles, then the stuff that goes over the curve is much less. And yeah, we're still missing out on areas, but they're much smaller areas. And if we made the rectangles even smaller, that would be a better approximation. So that's the general technique that we're going to use smaller rectangles. So let's revisit what the area of a rectangle is. Yes, welcome to calculus, where we teach you the area of a rectangle. So in case you forgot, which I don't blame you if you did, the area of a rectangle is width times height. So that's why we use a rectangle. It's really easy to calculate the area for. So the width of, and we'll use equal width rectangles for the most part. Sometimes we won't, but for the most part, we'll use equal width just because consistency. And we'll just say that the width of each rectangle is some quantity delta x, and a smaller value for delta x will produce more accurate results. So that's just taking a bunch of these rectangles and making them thinner. So that would be like here, right? Something like here, here, I don't know, just like making them thinner and thinner, right? We can see how that would be more accurate. The height of each function is f of x. Sorry, the height of each rectangle is f of x. Because it's defined, we make the rectangle, one of its corners, touch the function. So if one of the corners touch the function, then that's going to be its height, because the other corner is at 0. So the height will be equal to f of x. So the area of a single rectangle is that width delta x times f of x at that point. So with n total rectangles, where n is just some constant, the total area is f of some x1, perhaps here, where the function is evaluated at, times delta x. So that's f of x1 times delta x. So we get the area of this rectangle. Then we move on to x2. So that would be here. f of x2 is this height. Delta x is the width, so that's this much. We multiply those together and we get this area here, and so on until n equals 1 and n. So that's just the sum of a bunch of rectangles, and we can write that as a summation of f of x sub I times delta x. So that's our general summation formula for the total area. Wonderful. So we can evaluate area as a limit, and like we can try to figure out what will happen as the widths of the rectangles get really, really small. So we can take a limit of this sum, and we can see it pictorially here, what goes on. So if we have these really, really wide rectangles, you can see there's a lot of area that we're just missing out on, and a ton of area that's going outside of our bounds. So that's not good. But when we make it smaller, we're still missing out on some area, and we're still going over quite a bit, but it's not as bad as the first case. Even smaller, the amount that we go over is just not very much, and we're just missing out on smaller bits. And finally, this yellow picture here, we can see that we're barely missing out on any area, and we do go over, but just by a very tiny bit. So this is the idea, that we make the rectangles thinner and thinner, and eventually we get the actual area under the curve as the widths get extremely tiny. Yeah, so that's what we're doing here. We're taking the limit as n goes to infinity, so we want an infinite amount of rectangles. So that means delta x may be extremely tiny. We just want to fit an infinite amount of rectangles in there. So I have this video here. Let me try to get it set up, because I think this will be helpful to visualize what's going on. Okay. Let me just see what's going on. All right. Okay. So what we have here is, I'll just play this a couple of times. We have an axis and then some graph. That's the yellow graph. And we want to find the area in this certain interval. And what's going on is we're consistently drawing these rectangles underneath it. And we'll note that initially, right here, we don't have many rectangles. We have maybe, how many is it? Like 5, 10, like 12 maybe? I don't know. And we can see that we're overestimating the area at some points, but underestimating at other points. And we're just looking within this interval. But in the next step, we're going to create more rectangles. So we're going to make the rectangles thinner and have more of them. Okay, so I accidentally went a little bit too far. Here, yeah, so there's a lot more rectangles here, maybe like 24 or something. And now we can see our estimation of that area is a lot better. We're still slightly overestimating at some points, slightly underestimating at other points. Maybe those actually cancel each other out. Who knows? We can see that our actual area is getting very, very close to the area under the curve. And we do another iteration. So now we have like, who knows how many rectangles, 60, 100? And it's so close. It basically looks like we've just shaded everything underneath the curve. And we can do one more where it's very, very tiny, and that literally looks like the area under the curve. The amount that we're overestimating or underestimating is just negligible. So, but there's still rectangles. It's still a bunch of rectangles. It's just that they're very tiny. And I guess there was one or two more iterations. But yeah, here, they're so tiny. They're so thin. We can't even tell that they're rectangles anymore. But I assure you, they're still rectangles. Yes, they are still rectangles. They're just extremely thin. So now we can't even tell if we're making any error, because the error we would be making is so tiny. Let's just watch it one more time, and then we'll get back. So yeah, draw the function, have just a few rectangles, and then keep on splitting it up, and sure enough, we approximate the area very well. Wonderful. Let me just get back to where we were. Okay, so let's try to do a Riemann sum ourselves, and we are going to try to compute a left and right Riemann sum to approximate the area under the this curve, y equals negative x squared plus 2 from 0 to 1 using 4 intervals. Whoops, 4 intervals. So let's just do the left Riemann sum first. So this is a graph of our function. We're only looking in the white area, so the green and purple are out of our range. They're beyond 1 or less than 0. We need 4 intervals, so we need 4 rectangles, and we want to have equal widths. So we want delta x to be equal to 1, I guess 1 minus 0, that's the range of our interval, divided by 4 intervals. So we want delta x equals 0.25. So we can just like mark them here, that these are where the rectangles will be. Okay, so we want a left Riemann sum. So starting at 0, we can go up, and we want the left-hand corner to reach the function. So we're drawing the left-hand side right now, and boom, at 2, we hit the function. So the other side of the rectangle should have the exact same height. Should look something like that. And then we can draw our horizontals. Great. I'm going to change color so the overlap isn't as confusing. So now we need a rectangle right to the right of it. And we'll start with the left side. So we go up. We go up until we hit the curve, which is slightly lower than the previous one. And then the right-hand side should have the exact same height, so we can just follow it upwards. And then we draw the horizontal. So that's our second rectangle. Good. So now we go on to the third rectangle. We follow the left-hand side up and up and up until, boom, we hit the function. The right-hand side should have the same height, because it's a rectangle, and then we draw the horizontal. And then we'll do one more rectangle. So we go up and up and up until we hit the function here. The right-hand side should have the same height. Draw the horizontal. And here. I guess I forgot to draw this one. Right, so we want to find the area of these 4 rectangles. So, the first rectangle, I'll just call this A1, A2, A3, A4. So A1 is going to be equal to length times width. I guess let's do height times width. Actually, let's just change it up. Let's just do width times height. There we go. The width we know is 0.25, right? Each of these is delta x. All of these widths are delta x. So this will be delta x. Now we need the height. Well, the height is going to be this distance here, and that's based off of where we touch the function. So for the first rectangle, we have height equal to, maybe it's equal to 2, but it's really equal to what f of 0 is, right? We based it off of the left-hand corner. So we have a function of x, so let's figure out what f of 0 is. I guess I'll call this like f of x equals negative x squared plus 2. So f of 0 is equal to negative 0 squared plus 2, which is equal to 2. So this is going to equal 0.25 times 2, which is equal to 0.5. Let's do A2 next. Width times height equals delta x times f of something. What is that something? We look at the left-hand corner because that's where it touches the function. If we follow that down, that is right here, which is 0.25. So we want f of 0.25. So this will be equal to 0.25 times f of whatever it was. So this was negative x squared plus 2. So negative 0.25 squared plus 2. And this will be equal to 0.25 times 1.9375, I hope. And I don't quite know what that is off the top of my head, but we'll just leave it at that. Let's do A3 next, once again. Width times height, delta x times f of something. Once again, we're looking at A3 now. The left-hand corner touches the function, so that determines the height. We trace that downwards. We're at 0.5. So we come back here. This will be equal to 0.25 for delta x times f of 0.5. And this will be equal to 0.25 times, what is this, 1.75? And then we have one more, A4, width times height, delta x times f of 0.5, 0.25, whoops, I got way ahead of myself, not yet 0.5, we already did that. We're looking at A4 now. Once again, left-hand corner determines the height. We trace that down. Now we're at 0.75. So this should be 0.75. 0.75 squared plus 2. This will be equal to 0.25 times 1.4375. So now we can compute the total area, the total Riemann sum. Area equals A1 plus A2 plus A3 plus A4. So that will be equal to 0.25 times 2 plus 0.25 times 1.9375 plus 0.25 times 1.75 plus, it's a lot of algebra, but it's important algebra, 4375, and this will be equal to 1.7812. Okay, so that is that. That's only the left-hand side. We only did the left-hand side. We still have to do the right-hand side. So let's do that here. Once again, delta x should still remain 0.25 because we still want to do 4 rectangles. So let's just mark that, 0.25, 0.5, 0.75, and 1. So these are like where our rectangles will be. So now we're doing a right Riemann sum. So we want the right-hand side of the rectangle to touch the function. So the left-hand side of this first rectangle will start here, and the right-hand side will start here at 0.25. So let's start at 0.25 and trace our way upwards until we reach the function. And there we are, we hit the function. So the left-hand side should have the same height. We can draw the horizontal there. And same at the bottom. And then let's just change colors. We'll do the same thing. So the right-hand side of the second rectangle will start at 0.5. So we can trace that upwards until we hit the function. The left-hand side should have the same height. So we do that, draw the horizontals, and that's our second rectangle. Third rectangle, the right-hand side will start at 0.75. So we can trace that upwards until we hit the side. Left-hand side should be the same exact height. Draw our horizontal. And then one last rectangle should start at 1. We go up until we hit the function. Left-hand side should have the same height here and here. Okay, and we can do the same thing. Call this A1, A2, A3, A4. And we'll sort of generalize what we did before. So area is equal to A1 plus A2 plus A3 plus A4. So that's going to be equal to delta x times height of 1 plus delta x times height of 2 plus delta x times height of 3 plus delta x times height of 4. So we can factor out this delta x and we just have the sum of these heights. Right? So what are these heights now? Well, let's look at A1. This is its height. And that is determined by the right-hand corner, where the right-hand corner touches the function. So that would be f of 0.25, because f of 0.25 gives this function point. So h1 is equal to f of 0.25. H2, same thing. We're looking at the right-hand corner because that determines the height of the rectangle. That's going to be equal to f of 0.5. So f of 0.5. For H3, similar logic. This will be f of 0.75, and H4 will be f of 1. So that's our expression there. And you can plug in all of those values. This is 0.25 times 1.9375. Some of these we already calculated from doing the left-hand side. 1.75 plus 1.4375 plus 1. And this will give us 1.53125. Okay, great. So we've computed area twice. Let's just compare the values we got. So for a left Riemann sum, we got 1.7812, and the right-hand side we got 1.53. So the left hand was greater than the right hand. Does that make sense? Yeah, it should, because here we can see that we're overestimating. We have these extra areas here that we don't care about. Here, we're severely underestimating. We're missing out on these areas under the curve. So in the left-hand side, the red areas on the right are accounted for, but we go over. So it should make sense that the left hand is even greater than the right-hand side. So, and if we go back here, we said that on a decreasing function, a left Riemann sum is an overestimate, right Riemann is an underestimate, so we expect left to be greater than right. And maybe you're curious what the actual area under the curve is. Let's see, that should be equal to about 1.66, like 5/3. So that is indeed under this and above this. So indeed, this is an overestimate and this is an underestimate. Great. So, still quite a bit more to do, getting late, but we're going to keep chugging along. Another technique we can do is something called a midpoint Riemann sum. And this uses the same technique of rectangles. We'll still use rectangles, except in this case, the midpoint of the width of the rectangle touches the function. So previously, with left and right Riemann sums, we had the left corner touch the function, or we had the right corner touch the function. Now what we're saying is, hey, why don't we take the midpoint of the side, make that touch the function? Why don't we do that? And we can. So this type of Riemann sum both overestimates and underestimates the area. Like, for example, if we look at this rectangle here, we have this part that goes over the curve, but then we're missing out on some parts under the curve. So it's a little bit of both. So that's why, on average, it does better than left and Riemann sum. It goes over, but it also goes under, so sometimes it cancels out a little bit. So this is an even better approximation for area under a curve. But we can do perhaps even better using trapezoids. So this is the same technique as we did with rectangles, but now we're going to use trapezoids. And we do this by aligning both endpoints of the trapezoid with the function. So this is the trapezoid we're going to use, where we have some height or some width here. We have these two bases, and then we have these 2 points here that we're going to align with the function. And we can see this in the drawing here. I'll try to redraw the function because it being gray does not help very much. And we can see that, like, let's take a look at this function or this trapezoid here. This is one side, or these are two sides of the trapezoid. The base stays the same, and we align each endpoint of the sides with the function and then connect them with a straight line. And we can see, yet, sure, we still underestimate at points and we still overestimate, but the amount that we underestimate or overestimate is severely reduced. If we did a left Riemann sum, then this trapezoid right here, if it was a rectangle, it would look like this. And we would be missing out on all of this area. With the trapezoid, we only miss out on that area. So it's a much better approximation. And in case you forgot, may have been a while, the area of a trapezoid is 1/2 times the sum of the bases times the height, or the width in this case. But yeah, it's the average of these two bases times the height of it. Okay, so using the data in the table below, use a midpoint sum with 3 equal partitions to estimate the area under the curve. So it's very common that we're not given a graph and we're just given a table to do this. So we sort of have to work with the table and figure out what's going on. We could draw a graph if you really wanted to, but in fact it's probably better not to, just to get into practice. So we want 3 equal partitions. We're going from x equals 1 to x equals 7. So we need to partition this into 3 equal groupings. And yeah, those will determine like the bases of our rectangle, since we're using a midpoint sum. So the first rectangle can start at 1 and end at 3, right? You can imagine some sort of rectangle here. Whoops. That goes from 1 to 3. The second one can go from 3 to 5. Maybe it looks like that. Let me just bring this down a little bit. And then the last one can go from like 5 to 7. Right? And we have 3 equal partitions. Each one has width 2. And yeah, that would perfectly work. What's great about it is we're using a midpoint sum. And the midpoint of this first rectangle, if we start at 1 and end at 3, that'll be at 2. So that means this point here touches the function, just by definition of the midpoint sum. Similarly here, if we're on the second rectangle, the midpoint will be at 4, so that touches the function. And for 5 to 7, that touches the function. So we can see that, all right, this is going to be A1, A2, A3. These are just random rectangles I drew, not to scale whatsoever, it may not be accurate. But generally, we can see that area is equal to A1 plus A2 plus A3. So we're using rectangles, so that would be width 1 times h1 plus width 2 times h2 plus width 3 times h3. All 3 of these have the same width, so that would be 2 times h1 plus 2 times h2 plus 2 times h3. So now we need to figure out what are the heights. So we said the height will be determined by where the rectangle touches the function. And that's where the midpoint touches the function. So where f of 2, whatever f of 2 is, that is the height of the function. Let's just scroll back and take a look here, right? We have, let's just call this 1, let's call this 3. So our midpoint is 2. We look at where f of 2 is on the function. That determines our height. That is the height of the rectangle. We can see that we touch at f of 2, and that determines the height. The width is still 2 here. And even here, let's just call this like 7, 9, so 8. F of 8 is up here, and sure enough, that tells us the height of that rectangle. So to determine the height, we have to look at f of the midpoint of that rectangle. So the midpoint of this rectangle occurs at 2, so h1 will be equal to f of 2. So this is going to equal 2 times f of 2 plus 2 times, well, now we need f of the midpoint of the second rectangle, which will occur at 4. So this will be f of 4 plus 2 times, we need the midpoint of this third rectangle, which will be at 6, f of 6. and we are provided all these values in the table. So we can do substitutions. F of 2 is 5, f of 4 is 8, and f of 6 is 19. If we compute this out, this is what, 64? Yes, 64. And that is our answer. So yeah, we did not need a graph. I kind of drew one out just to visualize it, but for these, I encourage you not to draw a graph and plot points because that just wastes time. It's better to just go with what you know about how these rectangles are drawn and just go with the flow. Wonderful. This will be our last question of the day. We're going to do a trapezoidal sum, and it'll be very similar to what we did before. I'm going to hydrate. I've been talking for basically the last 6 hours. I was doing something before this that required me talking. So I'm going to lose my voice tomorrow. Okay, we want to use a trapezoidal sum to approximate the area under this curve on 0 to 2 with 4 equal intervals. So once again, we have the drawing here, and we have 4 equal intervals. So this is, it's up to 1, so this is actually a mistake. This should be 1. So that's my bad. Actually, you know what? Let's keep it at 2 and just pretend that this says 2 here, and this says 1. So that's on me. Actually, no, because I want to be consistent with the picture. So I'm going to go off of my answer key and say this is 0 to 1. All right, final answer. We'll stick with the picture. So we want 4 trapezoids, and we want them to have equal width. So what should our delta x be? We take the size of our interval, and we divide it into 4 equal parts. So this will be 1/4 or 0.25. So let's put markers indicating where we're splitting things up. Every 0.25, we draw a little marker. Okay, so now we draw our trapezoids. This base will stay the same. Now to draw these trapezoids, we go on either end of our markers, and we trace up until we hit the function. So for example, for the first side, we start at 0, and we trace upwards until we hit the function. Boom. Now for the right side, previously for rectangles, we just matched whatever the left-hand side was. This time, we're going to trace upwards until we hit the function ourselves. So we can see it's slightly higher. And now we're going to draw this side at an incline. So now we have a trapezoid. And what's great about this is now when we go to draw our next trapezoid, we start with this side, we go upwards until we hit the function. And sure enough, that's the right-hand side of the previous trapezoid. So that's great. So now we draw this other side. We keep on tracing up, boom, boom, until we hit the function. Let me try that again. I'm trying to get it to, whatever. There we go. So it hits the function, and now we draw the slanted line here. And then the base should stay horizontal, right? We want that to stay horizontal. Now we do the third rectangle. Once again, we trace upwards, and this is going to be the same side as before. And then we go to the other one, and we trace upwards, upwards, upwards until we hit the function. And then we have this different slant here, which happens to overlap the function, but it's not exactly the function. It's just I have a really thick line there. I'm drawing with a thick marker. And then one more trapezoid. So we trace upwards, hit the function, then on the right-hand side, trace upwards, hit the function, and we draw the horizontal. And we can see now that if we take these areas, it's going to be a really, really good approximation for the area under the curve. Yeah. So, let's do it. I'm going to sort of just move this over here since we don't really need that too much. So yeah, area should equal a1 plus a2 plus a3 plus a4. So that's going to be equal to 1/2 b, gosh, how am I going to do this? I'll call this ba1 plus bb1 times h1. So a and b are going to be two bases, and then 1 will denote which trapezoid we're looking at. So for the second one, it'll be 1/2 ba2 plus bb2 times h2. And then same thing carries here. h3 plus 1/2 ba4 plus bb4 times h4. Okay, beautiful. Let's take a look at it one component at a time. Actually, I don't even know why I wrote this equation, but okay, let's just look at a1. 1/2, oh boy, don't know what happened there. 1/2 ba1 plus bb1 times h1. So, what is ba1? So ba1 is one of these bases. So let's just take the left base. That is determined, the height of that is determined by the function value of the left-hand side, which starts at 0. Remember, we traced up starting at 0 until we hit the function, which occurs at f of 0. b1 is the height of the second base. So that starts at 0.25, and then we trace upwards until we hit the function. So that will be of length f of 0.25. So this is going to equal 1/2 f of, 0 plus f of 0.25 times the height, which in this case is this bottom part here, which we said was 0.25. Right, and we can compute this, oh goodness me. This is going to be equal to 1/2 times 1 plus 1/16 plus 1 is 17/16. Do I want to write it in decimal? No, I don't. Times 0.25 is 1/4. Do I feel like continuing to do this? Fine, okay. This is going to be 1/8 times 33/16. So 33/128. I believe. I don't know. It's midnight. So hopefully that's correct. These next few are going to be tougher. So 1/2 ba2 plus bb2 times h2. So what is ba2? Well, that's this side right here. Perhaps I'll just choose the left-hand side. And that's the same thing as bb1, right? We just looked at that here. We said that was at 0.25. We traced upwards until we hit the function. So that's going to be equal to f of 0.25. So this is 1/2 f of 0.25. And then for the second base, we look here. And this is going to be, you guessed it, f of 0.5. Right? And then once again, we multiply that by 0.25 for the width. This is going to be 1/2 of, 17/16 plus f of 0.5 is going to be 5/4 times 1/4. So this is 1/8 times 37/16, I hope. So that will be 37/128. Let's do A3. Can speed through this one, hopefully. BA3 plus BB3 times H2. So that'll be 1/2. This first base will carry over from the previous one, so that's going to be f of 0.5. And now we have this new base to consider. We traced up from 0.75, so this height will be f of 0.75. And then once again, we multiply that by 0.25. So this is 1/2 times 5/4 plus f of 0.75 is 25 over 16. And multiply that by 1/4. This is going to be equal to 1/8 times 45 over 16. So 45 over 128. One more, we got to power through it. 1/2 BA4 plus BB4 times this should be H4. This should be H3 here. H3. This is 1/2 BA4. That's this side right here. That carries over from before. So this is f of 0.75 plus BB4 would be this height here. We traced up from 1, so that height is determined by f of 1. So f of 1 times 0.25, 1/2 times 25 over 16 plus 2 times 1/4. This is equal to 1/8 times 57 over 16. That's equal to 57 over 128. So now we can find the total area. Total area equals A1 plus A2 plus A3 plus A4. This is equal to 33 over 128 plus 37 over 128 plus 45 over 128 plus 57 over 128. What is this going to be equal to? 172 over 128. What does that reduce down to? We can figure that out just for fun if we want to. Because I'm curious now, 43 over 32. And that's going to be approximately 1 1/3, so 1.33. If we're curious as to what the real value is, it will be actually it is exactly 1 1/3. So the exact value is 4/3, right? This is equal to 1.333. Let me just calculate what 43 over 32 is. 1.34375. So we can see we are extremely close to the true value using this trapezoidal approximation. And sure enough, you can see that there's very little error. We're just slightly going over in these places. Here we're basically overlapping the function. So the trapezoidal approximation gives us such a good approximation of the true area. So that's what Riemann sums are. We're taking these shapes, whether they be rectangles or trapezoids, and we're taking a bunch of them with tiny widths, or in this case, maybe larger widths, and we're just taking the area of these individual shapes and summing them all together. Just as we would do with something like this, where we split it up into shapes we're familiar with, we do the same thing, except we just make these shapes really, really thin. That's all that Riemann sums are, and there's different ways of doing it. Using a left Riemann, a right Riemann, a midpoint Riemann, where's the midpoint Riemann? Right here, or trapezoidal. They do require a lot of arithmetic, I won't lie about that. But seeing how close we are to the actual area under a curve is exhilarating. And in a future lesson, we'll be discussing why we care so much about the area under a curve. Right now, it just seems arbitrary. Like, why are we doing this? It'll matter quite a bit later on, and the applications are endless. So, hopefully you enjoyed today's lesson on Riemann sums. I had a blast teaching you, and yeah, I will be back again next week with some more calculus stuff. We'll continue with this. Next time we'll be talking more about integrals, computing integrals, so that should be exciting. So yeah.